Everyone, thanks for coming. Sorry I was a few minutes late, but happy to be here. And today I'm going to be presenting about augmenting static analysis. So how many people here have reverse engineered or used IDA? That's great. And so this is all about improving and extending how you can use IDA to reverse engineer. And the inspiration for the talk, it kind of came back to when I first was learning how to reverse engineer. I got to learn in an environment where I was surrounded by a lot of really interesting people. They loved their work, and I found that very inspiring. And so that's what got me into security. And that also gave me the ability to ask smart people questions. And I don't know if you guys have reversed a lot of C++ code, but just when I was getting comfortable reversing C, I started to pick up some C++ code, and I came across an indirect call, like call EAX. So I was like, well, how do you know what EAX is? So I walked across the room and I asked my brother, and he's like, oh, that's a virtual call. You're going to have to go and reverse the class structure, or you can use a debugger. So that's kind of the original reason that I wanted to create this tool, to do things like automate that process for me, because it gets tedious pretty quickly. So when I heard about Pintool, I thought that's a great opportunity to make it super simple and easy to do things like resolve virtual calls. Pintool, if you guys aren't familiar with it, it's a tool for binary instrumentation. Now what that means is they're just going to modify a program at runtime. So it allows you to insert your own code. Ablation is a tool that I built on top of Pintool that extracts information from the process as it runs. And it was designed to simplify the process of reverse engineering, to take the headaches out of trying to reverse class structures when you're not even sure if you want to yet. But then I found that you can also use it to find interesting code to audit. And this I'll get into later, but I call it ablative fuzzing. And essentially it's trying to find interesting code using existing samples out there. Now, where is it useful? As I mentioned before, it's useful with C++, especially if you're newer at it. You can feel a bit overwhelmed if, say, for instance, you're dealing with MS-HTML. That has 78,000 functions in it. Or Chrome Child, that's 202,000 functions. Where do you even start? So if you're new on or dealing with something like MS-HTML or Chrome Child, it can be a bit of a pain. It can be a little overwhelming. So using Ablation, it kind of gives you the illusion that you're in control. So it's a little motivating. You kind of have a little bit of guidance, and you don't have to worry about every little virtual call out there. You can use existing samples to get yourself going. So here, if looking at this slide, can anyone have a clue what this does? I don't. But you could probably go through, reverse the class structure and figure it out, or using Ablation, you can really quickly resolve those calls, and then it looks something like this. Well, now we have some context. We kind of have an idea of what it does. It's dealing with polygons and triangles, rectangles, etc., but we're dealing with shapes there. Something also that's great is when you resolve virtual calls, it creates you interactive cross-references in IDA. So you can actually look at the cross-references to a call that you would not be able to before. And it will show up in the graph view, etc. So it extends the interactivity of IDA. Now, to use Ablation, it's actually super simple. You just give it a module that you're targeting and you let it go. And then you have to go and run through some samples, exercise the code. Thank you. Now, what information can we gather at runtime? We could do things like save control flow data that we can look at later. That's the basic blocks that get executed. The frequency at which they execute. The virtual calls and their targets. We can do things like identify interfaces that are being called externally. I'll get into how that works. And once you have all this information, you have to use it for something, otherwise what's the point? I imported it into IDA using a script. So it's very portable. You don't have to have any extra tools. You don't actually have to run any code on your system to use it properly, which I really like because running random code, well, we are in the security industry, right? This is a snapshot of it gathering control flow data. Now, this is a Firefox in the background, and this is Ablation printing it out. So these are all basic blocks that are getting executed. Here's a virtual call that has been resolved, and this is a virtual call that was to an external module. Now those you can't really resolve in IDA, but it fills in the comment saying exactly what call it is, which is very useful. Now at runtime, this is kind of key here. The first time a basic block executes, we save that, but only the first time. If you tried to save every basic block every time it executed, you'd end up with an enormous amount of data, and I doubt it would be very useful. But by doing only the first basic block, we can do things like create a set of basic blocks that are tied to a sample. So sample A maps to a set of basic blocks within the module. And we're essentially looking at a subset of the total basic blocks in the module. But you can use this to compare samples and see if they actually do something new. And when you import the information into IDA, it ends up looking a lot like this. The green highlighted sections are basic blocks that have been exercised, and you can see it jumped over that one. And off to the right, you can see some virtual calls there that have been resolved. Now, I went through a bit of a process trying to choose the colors for, how to represent it. What I found was if you picked annoying colors, staring at it for hours, well, that gets irritating. So you want to pick something that's kind of passive, not really going to distract you, and that way after a while you start to absorb the information just as you're reversing in IDA, and you don't even need to think about it. So it may seem like minutia at first, but it's important not to annoy people, right? Now, when it comes to actually resolving virtual calls, the way that I do it is instrumenting the process for every indirect call instruction. I maintain a list of the observed targets. So if you have, well, here we have four different calls that have been resolved. Or sorry, 4 different targets. And we also know now that there's 4 different types there. We can infer that they're all related. And we save this information as the process executes by running different samples. So we can tell if, a sample is using a specific type of object, and kind of where samples differ. Now, every time that virtual call does get executed, we look at the previous list, and if it's already in the list, we just ignore it. But if it's new, we save it. So I think I'm going to show you guys real quick here just how simple it is to use the tool. And in order to do that, I'm just going to go through the whole process of downloading Pintool and running a sample and then importing it into IDA. Now, has anyone here used Pintool before? Pintool, it's great. It's really easy to use. I really like it. There are some alternative products. I know of Dynamo Real, and I think there's another one I forget. But there's a few out there that you could use for the same purpose. Now, Intel makes it free for everyone, which is great. I think it was developed at the University of Colorado. Let's see here. Okay. So when that's done downloading here, I actually have it already set up in the VM. So you can go there, you grab it, you extract it in the VM, and then you copy in just the module. Now, this module, you can get it. It will be signed, but I suggest you build your own. It's pretty simple. We're not going to go through the process, but once you have the module there in the VM, I'm going to run it against Internet Explorer. And we're going to look at, do you guys remember VML? Microsoft's vector graphics library. So it's pretty much like it, I think it's long dead, but it is still supported. There have been a few bugs in recent years, and it was like they wanted to compete against SVG. And then Microsoft went and added SVG support to IE, so VML is a little bit deprecated, which makes it a good example here. So you just have to specify the tool and then the module. The module's name is VGX, and then a double dash for the process. Then I'm going to give it the site. And we'll let it go. Now what we're going to see here is Internet Explorer load. I'm using a build of Internet Explorer Preview because it's a single process and it renders all in that same process, which makes it easier. You can specify a process ID, but for the sake of simplicity, it's nice and easy. So now I'm running the samples off of a virtual machine here. So it's a Linux server. And when it loads, we're going to see when VGX loads. and we're also going to see the code that gets executed. We're going to see basic blocks as they get rendered there, and virtual calls being resolved. And then we're going to import that information into IDA so that we can actually use it. Now, I find that using this tool, it saves me a lot of time, especially when I'm looking at newer versions of something that I've looked at before. So we rendered some VML, and then we're going to close it. And the result here is just a Python file. That when we have IDA open, so right now we can see on the left all the functions in here. Now running this file here, I'll show you briefly what it looks like. It has a header which is a script just for importing the data, and then it just scrolls through all the different pieces of data to import. Now when I run it, it'll probably take a few seconds, and the result is now we can see the code that got executed. Consider that most of the code that runs is things that is going to be shared by a lot of samples. So if we run a really simple sample, just like the most basic one, draw yourself a circle. It's going to show us the code that's involved in drawing a circle. But that's also going to be involved in drawing, say, a path or fonts. That code isn't going to be very interesting to audit. What you can do is if you diff the two, say we render that circle and we render, say, a text path, and then we find the code that is exclusive to the text path, well, now we know we can start auditing this, and we're going to be looking at code that's relevant. On the left, you can see all the functions that got executed, and if we were to look at some of these, there we go. Okay, so this virtual call here, it probably would have been not too difficult to figure out if we were using a debugger, because it looks like they're pulling it from a global. But if you're new out or you haven't reversed C++ in a while, it's a pain in the ass, and you might just not want to do it. Motivation is key when you're reversing, because you have to want to do it. We can look at these. We can look at cross-references to it. So there's only one, but if we wasted a whole bunch of time reversing that and it was just really boring code, well, that'd be annoying. But just very simply, we were able to pull all this information out of the process, and now we can use it in IDA. And I really love the portability of it, the fact that you can run it in a VM and you don't actually have to run any code on your system. So that's briefly how to use it. There's another demo later that shows it a little bit more in depth. Now, how Ablation augments static analysis, we've already discussed this a little bit, but it avoids the tediousness and things that can be automated. Well, they should be automated. It adds context by showing you what calls are operating on which data, and that allows you to understand quicker what you're looking at. If you don't have symbols, sometimes it can be really hard just to get started, to figure out, okay, well, what's this actually doing? But if I can see all the other places where this code is used, if I can compare a couple of samples and then add some context to it. Then you can actually get going and start to understand what you're looking at. And that's where you gain traction. Now, it improves the interactivity of the IDB, cross-references. It's actually quite useful because if you find code that might be vulnerable, it's annoying to go and try and find every place where this code has been used. But if you can just look at the cross-references and check for, say, a size comparison, well, that would really speed up the process of assessing whether it is a problem or not. Now, adding trace info. I honestly don't find traces very useful by themselves. There's often too much data, and it's just not something you can make use of. You can use it as a trace, but that wasn't the original intention. The trace info is displayed there to help the user understand the flow of data and the flow of code. And if you actually think about what's shown, that also includes what's not shown. So you can see that if you have a feature here and it has chunks of code that was never executed, but you ran your test samples over it, well, why wasn't that code executed? Maybe it's an undocumented feature, or maybe it's an incomplete sample set that you're using for your development. A good example would be a media codec. So you have code for processing an MP4, but your test samples, they're not going to be massive files, I imagine. They're probably going to be a meg or two, because you don't want to lug these things around. But what if your codec treats like a streaming 4 gig file differently than a 1 meg file? Because the 1 meg file will be downloaded before you even know it, but if you're streaming 4 gigs, there might be a feature to buffer that, and that might end up being used. So you can tell that, well, this feature here has not actually been tested with our sample set. Or if you're auditing for bugs, well, why wasn't that executed? Maybe it's more interesting. You can also do things like infer inheritance info, determine that things are related to each other, and come to understand the different objects that you're working with. Now here, it's pretty obvious by looking at this, we're dealing with shapes and a generic parent class, but if we didn't have this, well, we might have to spend a fair amount of work to figure out that it's not something we want to look at. At the very least, we know here that these are all related. So now, observing live execution, this is kind of a fun little thing that I did that turned out to actually be a little bit useful. But when you observe something on a computer, it always ends up looking like the Matrix. And it's like, oh, cool, but what's the point? It's not very useful. Now, the reason why you can actually make sense of this is because if you run several samples, the rate at which new basic blocks end up being executed, it decreases greatly after the first few samples. Most of it is initialization, and then you end up with specific code for each sample. But the more samples you run, the fewer basic blocks you actually see. So this actually allows you to watch the process in real time, and you can do things like tell that, oh, I've run a whole bunch of samples, but I haven't hit any new code for a while, and then all of a sudden you run a sample and you do hit something new. Well, maybe that sample does something that's uncommon or a bit different. Maybe that sample's worth looking at further because Well, if you're rendering just a circle, really, who cares? I like to use this feature to find unique samples, cool samples, samples that aren't just your generic thing that it's the first link on Google. And using this tool, it's actually a lot easier than trying to dissect all these samples or diff them or however you would have done it before. Now, if you run over a sample set and then let's say you were to fuzz this sample set, you can tell when you've actually done something new as well. So if you fiddle with things, it will show you that here's a place you might want to look. And if you're really lucky, it might be an undocumented feature. Now, I love undocumented features. They are great. They contain lots of bugs. This is actually where the name of the tool comes from. Now, I don't know if you guys know, but ablation, it's kind of weathering something down over time. It's a little bit like erosion. I like to think of it as you're weathering down the module. You're breaking away the stuff you don't want to look at. Now, I'm going to show you guys it actually looking at Firefox in real time here. We're going to be looking at their WebGL library, so shaders and the like. So we can see all the modules that get loaded. I added the verbose flag. Usually that's not there, but it's nice to see. We can tell when our module gets loaded, and we're going to run it through a few samples. And you guys are going to see that the basic blocks, they decrease when we run more samples because, well, they're quite similar in the terms of code they execute. And you'll actually be able to recognize names of functions and, you know, well, maybe that's something I want to look at. Or, no, that's boring. Okay, here we go. So I downloaded the WebGL conformance tests. This is what the developers use, right? This is what they're using to test their code on a daily basis. And if we run that entire set, we should have a pretty good idea of exactly the code they test. And we're not going to run the whole set right now because that would probably take a few minutes, but we can see that this code here is all initialization. We haven't even done anything interesting yet. And once we start running a few samples, I like to think of it as we're weathering away the actual code that we don't have to look at. There's a lot of code out there, and if you can improve your efficiency, you're gonna find more things. You're gonna enjoy it more as well. So we're going to run this first sample set. It looks like they're looking at attributes, but all right. Here we go. So now we've got some samples running. We can tell what code they exercise, and there's a lot of stuff coming up. It's probably iterating over a few samples now, and it's slowed down a bit. Now this little box here, it's for changing the color that you're shading things in with, right? Because we've run the initialization code, maybe we want to color that in as gray, so it's not so interesting. Maybe we want to color in code that's related to specific shader features as another color, so that when we're going over it, we can say, oh, I know where that's from. So to show you guys, I'm just going to change the color to a blue. Now all that actually does is it adds one line to the script so it changes the color, and anything that comes after that, well, it will be shaded in like that. So now we run a few samples. It looks like things are slowing down a little bit. If you make your way through the whole thing, by the end, you're barely hitting anything. And that actually, I think, is where something interesting happens. Because when you're barely hitting anything, you've covered most of their sample set. And you can use that information to find really interesting code to audit. We can also tell that, well, the code that has been run, we don't want to look at it. Or maybe just not as much. Now, when we run it, you'll see certain features have been exercised, certain ones haven't, but this is where the fuzzing comes in. Now, it's a term that I call ablative fuzzing. And it makes use of what I call an X sample. And it's really just the set of basic blocks that a single sample executes. Now, if you think about it, you can have different samples that have the exact same X sample. For example, rendering 2 circles rather than 1. Now, you can also do things like, well, does a comment tag change the way HTML is rendered? Well, I mean, it shouldn't, but it does. That's kind of interesting. Very simple example, but you can see how some things that, if you were to diff, wouldn't necessarily show up as different samples. It allows you to highlight where samples actually diverge, which is useful if you have related samples. Say if you had samples that were fuzzed. Well, you're fuzzing from one sample to another. Let's say you end up with a crash. You can find out how you got there, but not only how you got there, why you got there. So different ways that ablation can be used: calculating coverage for a sample set, highlighting untested features. Now that's when you run through like an entire test suite. Auto-generating new samples. I actually did this. It worked out pretty well, but I wasn't looking to generate actual test samples. I was looking to generate samples that get me to certain areas of code. Crash analysis. Trying to assess how it crashes, it would be really simple. You run 3 samples. The first one, let's say you had an HTML crash, you'd run a hello world sample. That's your initialization code. Then you run the parent to the crash sample, so you get pretty close. And then you run the crash sample. Anything that happens after the parent sample is very likely related to the crash. And I've used it to figure out why programs are crashing really quickly, when sometimes if you have a fuzzed sample, it can take you ages. Determining which code determining which code processes specific data, like SVG in Internet Explorer. Capture the flag. Does anyone here like playing capture the flag. Yeah. So capture the flag, I've actually used it to breeze through some samples because in capture the flag, a lot of the times, there's just extra code around it that never gets run. Well, you can see exactly what gets run and decide where you want to go on. Exploit analysis. Just last weekend, I was looking at a Flash exploit, and actually, what I thought was going on, I realized wasn't quite accurate when I saw a virtual call resolve to both something in Flash and virtual protect. Well, that's pretty odd. Turns out they just corrupted a pointer and used Flash functionality to call virtual protect. So now ablative fuzzing is fuzzing what not to audit. Now, why do people audit? It's how you find the good stuff. Why do people fuzz? A computer can work while you sleep. I mean, that's a pretty great idea. Researchers tend to prefer one or another. I've always been an auditor. But I think a combination of the two could be even better than just one alone. Take, for instance, if you try to hide a bug in one slide, well, anyone's going to find it. But if you hide it in 100 slides, well, that's a little different. Now, if you fuzzed those code samples and you didn't find the bug, you would see what code was tested. It would make sense to start on the slides that were not tested. You might still have to go through all 100 samples, but if you found it in the first 10, wouldn't you be happy that you started there? And this brings us to the fact that highly traversed code is not particularly interesting. We went over this circle versus animated font sample. Well, the code that they share, I'm not all that interested in. And my time is better spent elsewhere. That circle element, it also shares code with a bunch of other samples. Now, if we look at infrequently executed code, that's a lot more likely to contain bugs. Now, ironically, I actually have found a bug in an SVG circle element, but that's the exception, not the rule. So by diffing the two, you can exclude the code that they share. Now, if you use Ablation to traverse a sample set, like an SVG test suite here, you have a bunch of common samples. If you take those samples and you fuzz and you hit new code, well, you're moving off this baseline. Depending on your fuzzer, it might work great. Chances are that it won't. But you're going to look at new code that goes beyond their sample set. Now, I like to use gray to show code that was run during initialization. I like to use green to show the sample set. And then blue represents the fuzz samples, something that's new, right? We mutate those samples when we get to new code. But the most interesting stuff is the stuff that's not colored in. It's adjacent to the stuff that's colored in, especially adjacent to the fuzz samples. This code, it's not really tested out there. You got to it through some sort of a mutation, but their entire test suite doesn't touch it. This code's going to be less scrutinized. Maybe it's untested, undocumented, or experimental. But the SVG test suite didn't hit it, which means they haven't been testing this code. This code here specifically, it's from MSHTML's SVG rendering. Now, I don't know exactly what this does, but I fuzzed it and hopped over this. Well, this call here interests me. I'd like to know what that is. If you're looking at C++ code, you can also include methods from other classes there that are colored. So to summarize, it's excluding code to audit. We're fuzzing to find code not to audit, and then we can go and actually look at the code as, because I don't think you're ever going to replace people. So you can use things like a genetic algorithm to find cool code to audit. Now, what can we take away from this? Honestly, I find myself using this tool because it saves me time, and it's easy to use. So I hope you guys will give it a try, but it doesn't do the interesting work for you. It might help you get there. So thank you. Anyone have any questions? Yeah. Oh yeah. So you can diff runs. Oh, right. Is there support for diffing runs already built into the tool? The simplest way to do that is to run one sample, then just change the color and run another sample. You could run 2 different samples and diff those, no problem, but the support is there. You won't have to go and do it manually. Thank you. Yes?
So this tool looks a lot like the dye plugin that were introduced to Recon last summer. Are you familiar with that?
No, I haven't. Sorry, it's called the dye plugins?
Yeah, I haven't come up with the dynamic IDA execution.
So I know that there is an IDA pin tool for trace execution. I haven't actually used it myself. Honestly, when I was trying to test it out, I got irritated with how annoying it was to get started. I'd be really interested to see what they've done there with these dye tools. I'll have a look at them. Yeah. All right. Thank you guys for coming.